I'm going to get started. So, the last set of worksheets and the last homework are due on December 2nd. So worksheets 23 through 29 are due on December 2nd, and homework number 4 is due on December 2nd. Exam number 4 will also be December 2nd. That is not the end of the semester. We still have a little while after that. After that, starting the Thursday of that week, we will have presentations. I'll get a presentation schedule up by the end of this week, the order in which people will do presentations. I'm just going to randomize the list of people in the class. So the presentations in your papers are due on the 4th. Make sure your topic's been accepted. I think that's true for most people in this class. Write a 2 to 3 page paper on the topic, answering the question or discussing, going over the topic, and a 4 to 8 minute presentation on the topic. The presentations will be on the 4th through the 11th. They will be in class. Make sure you have your slides ready to present. And yeah. So you can either have your slide, make sure either you have your slides on like a USB stick or something, or you've submitted them in a format I can download in advance, something like that. Something where I can get them in a format that I can actually use on the computer. So preferably use PowerPoint. You all have access to it through city colleges, so you can use PowerPoint that way. Lastly, if you missed the test, because there was a non-trivial number of people who missed the test, I've already contacted all of you, but please just see me before class or after class, and I can set up a makeup for you. You need to be here in person to make up the test, but you can take it during class or after class. So just talk to me about it. I've got everything ready for it. Okay, let's continue talking about black holes. So, we mentioned that black holes have 3 properties. They have mass, which is, how much matter they contain. They have an electrical charge, a net positive or negative charge, and they have an angular momentum, how fast they spin. These 3 properties determine all of the features of a black hole. Theoretically, all the matter collapses down into like a point where space and time no longer exist, but it's questionable if such a thing actually exists. This is one of these places where one of our theories of the universe doesn't mesh with another one of our theories of the universe. So clearly, our understanding is incomplete. And this is one of the more extreme situations where we really don't know what's going on. So what would it be like to visit a black hole? So at a black hole, the curvature of space-time gets greater and greater as we approach the black hole. And the black hole is effectively a bottomless pit in space-time. It's a singularity in the mathematical sense, which is one of those points that goes off to infinity in math. But there is a cutoff. There's the event horizon. There's a point of no return. So a trip into a black hole, if we were watching someone enter a black hole, what would we notice? As someone entered a black hole, we would see them slow down from gravitational time dilation, appear to slow down. Their clocks would run more slowly. We notice a gravitational redshift. They'd redden, and they would appear to stop. Well, they would appear to vanish at the event horizon because they redshift beyond what we can see. But basically, they'd appear to stop the event horizon. To the astronaut, everything would appear normal as you cross through the event horizon. Well, depending on the size of the black hole. If it's a really big black hole, everything can appear normal as you cross through the event horizon. If it's a small black hole, you'll be torn apart by tidal forces in an extremely painful manner. So you'll notice that. But that would happen even towards a neutron star or something like that. So here is sort of an idea of what would happen as you approach a black hole.
In your textbook and the chapter overview video, we've discussed the strong evidence indicating that black holes really exist. But what exactly is a black hole, and what would it be like to visit one? We'll consider these questions in this video. The idea of a black hole was first suggested more than 200 years ago based on the possibility that there might be objects with an escape velocity greater than the speed of light. Recall that escape velocity is the speed that an object must have in order to leave orbit of a planet or other object. For example, the escape velocity from Earth's surface is about 40,000 kilometers per hour, or 11 kilometers per second. However, if we could somehow shrink Earth in size, the strength of gravity on Earth's surface would grow stronger, making the escape velocity larger. In principle, there is a size at which Earth's mass would be so compressed that the escape velocity would exceed the speed of light of 300,000 kilometers per second, in which case not even light could escape from the surface. This captures the basic idea of a black hole as an object with gravity so strong that not even light can escape from it. The boundary within which light cannot escape is called the event horizon, which marks the place at which the escape velocity is the speed of light. However, rather than being the surface of a highly compressed object, the event horizon hides everything within it, and all the mass has in principle been crushed to the point we call the singularity. Moreover, we now understand black holes in terms of Einstein's general theory of relativity, which tells us that gravity causes distortion of the structure of space and time, or space-time. We cannot visualize all four dimensions of space-time simultaneously, so we instead use two-dimensional analogies. We begin with a flat rubber sheet, representing space-time far from any massive object. A massive object, like a star, causes space-time to curve, much like the rubber sheet would curve with a heavy ball placed upon it. The denser we make the ball, the more it will curve the rubber sheet, and in our analogy, a black hole is a bottomless pit in space-time, with the event horizon marking the boundary from which nothing, not even light, can escape. Keep in mind that the rubber sheet is only an analogy meant to illustrate the extreme distortion of space-time near the event horizon. In reality, a black hole is spherical, as we see in this computer simulation looking toward a black hole with stars behind it. The strange arcs of light and double images of stars are caused by the way the black hole distorts space and time. We usually describe the size of a black hole by what we call its Schwarzschild radius, which is the radius its event horizon would have if we neglected the distortion of spacetime. It is given by this simple formula, 3 kilometers times the mass of the black hole in solar masses. For example, a 10 solar mass black hole would have a Schwarzschild radius of 30 kilometers. Before we continue, check your understanding of the formula, which we have moved to the bottom of the screen, by answering this question. What is the Schwarzschild radius of a 1 billion solar mass black hole? Would it be 1 billion kilometers, 3 billion kilometers, 300 billion kilometers, or 1/3 of a billion kilometers? The answer is B. We simply put in 1 billion for the mass in solar masses, and multiplying by 3 kilometers gives a Schwarzschild radius of 3 billion kilometers. We chose these examples to illustrate the fact that there are two general categories of black holes known to astronomers. The black holes that form when massive stars die in supernova explosions typically have Schwarzschild radii of tens of kilometers, or roughly the size of Rhode Island, the smallest state. But we also find supermassive black holes in the centers of galaxies, and some of these have masses a billion or more times that of the Sun, giving them Schwarzschild radii as large as the orbits of the outermost planets in our solar system. For our final topic in this video, let's turn to the question of what it would be like to visit a black hole. We'll assume you are visiting a black hole formed from the death of a star, and not in a binary system like Cygnus X1, in which radiation from the accretion disk might quickly kill you. This animation imagines that you are orbiting the black hole while another spaceship is falling toward it. Notice that as you watch the second spaceship, you'll see its time run slower and its light become more redshifted as it approaches the event horizon. In fact, you'd never actually see it reach the event horizon because its time would in principle come to a stop at that point, and its redshift would grow too large for it to be observed by any conceivable technology. However, a person in the spaceship falling toward the black hole would not notice anything strange about his own time, and in fact, he'd very quickly fall past the event horizon and into the black hole. Unfortunately, he would not survive the journey because the enormous mass and small size of the black hole means that gravity would be significantly stronger at his feet than his head, creating a lethal tidal force. The only known way that a person could in principle survive the journey across an event horizon would be if the visit were to a supermassive black hole, where the larger size would mean a much weaker tidal force. Still, according to current understanding of physics, no communication is possible from inside a black hole to outside it, so a traveler who crossed the event horizon could never tell the rest of us what he saw inside.
So, the general thing with a black hole is gravity-wise, they're the same as anything else far away. They only get really interesting when you get close to the event horizon. A few times the sort of shot radius. So if the sun, for example, shrank into a black hole, its gravity would be different only near the event horizon. And the sun as a black hole would not be very big. It's only 3 kilometers in radius, so the weird gravitational effects for a black hole don't really kick in until you're pretty close to the black. Again, a few times the sort of shot. Black holes don't mystically suck in material any more than an extended mass would. Anything with the same mass has the same gravity far away. It's just when you get close, you get some weird distortions because of the extreme bending of space-time. One of the major effects of a black hole, or actually also a neutron star, are tidal forces. So the tidal forces near the event horizon of a 3 solar mass black hole would be quite lethal to humans. And the tidal forces are actually more extreme near smaller black holes because there's a bigger change in gravity over the length of your body. So there's bigger tidal forces. Because, the length of your body is closer to the radius. So if you have a really big black hole, the changes aren't as dramatic. So tidal forces would be gentler near a supermassive black hole because its radius is so much bigger. But it has to be really big. And as you approach a black hole, you would undergo what's known as spaghettification. The black hole will exert tidal forces, which will tear you apart. Forces on the feet would be stronger than on the head. This would stretch you apart and eventually rip your body to shreds and reduce you to a stream of particles. And this is actually less for a larger black hole. So a small solar mass black hole would tear you apart, but you could cross the event horizon of a supermassive black hole without knowing it. In reality, you'd be dead before you got to the event horizon because most supermassive black holes are surrounded by super hot energetic accretion disks, which would cook you. But these tidal forces are important because they tear things apart and help generate these accretion disks. So matter encountering a black hole will experience enormous tidal forces that will both heat it up to radiate and tear it apart. So it heats things up, tears them apart, and you get these accretion disks around black holes. Additionally, there's something called gravitational redshift. Light takes extra time to climb out of a deep well, a deep hole in space-time. This leads to what's known as gravitational redshift. The light gets stretched out because it needs to be lower energy, but it can't lose that energy by slowing down because it always travels at the speed of light. And so that effectively causes this gravitational redshift. We have observed gravitational redshift, I believe, from neutron stars, which have the advantage of actually, emitting light, unlike black holes. It would be more extreme in a black hole. It's the most extreme in a black hole, but generally you don't see things, it's hard to see something just directly falling into a black hole. There's also gravitational time dilation. The other way to think about gravitational redshift is that from your point of view, time passes more slowly at the event horizon, so the waves travel more slowly, so the light coming from it is brighter. That's gravitational time dilation. Time is relative. Now, if you travel near the event horizon of a black hole, some probe near the event horizon will be seen by observers as experiencing a dramatic redshift as it gets closer. So it appears to be going more and more slowly as it approaches the event horizon. This is the gravitational redshift. It's not due to motion, but to the large gravitational fields present. The probe itself, from its point of view, doesn't experience any shifts. Time would appear normal to anyone inside. This is why you could get, this is sort of this effect of getting close to a black hole in your time slowing down compared to someone who wasn't getting close to the black hole was a major plot point in Interstellar, I believe. They slingshot around a black hole, but they got so close to a black hole that it, they ended up coming back much later because of that kind of thing. Similarly, a photon escaping from the vicinity of a black hole will use up a lot of energy. It can slow down, but it can get longer and longer wavelengths. So that's what happens. We get what's known as gravitational redshift. So we don't know what's inside a black hole. In fact, what we do know is that it cuts itself off from the rest of the universe. So we can't really know what's inside a black hole. So present theory predicts that the mass collapses until its radius is 0 and its density is infinite, which is insane. And this is one of the problems with present theory. Like it's a solution to the equations of general relativity, but it's nuts. This is unlikely to be what actually happens because it's insane. But we don't know what happens in such extreme conditions. And this is dealing with something that is both very small and has lots of gravity. So this is a classic case where you're dealing with both quantum mechanics and general relativity, and those theories don't mix well. We do not currently have a theory of quantum gravity. And so until we understand how quantum gravity works, we will probably not have any better idea of what's going on inside a black hole. But because this is one of the big unsolved problems in physics, people are working on it. Just haven't solved it yet. So another question you might ask is, these things seem insane. Do they really exist? Well, yes. We have identified a number of black holes in a number of ways, and recently we took pictures of a couple of them. So one of the best black hole candidates out there is Cygnus X1, which is the unseen partner of a star in the constellation Cygnus that is emitting X-rays, has a mass that is about too big to be a neutron star. And really looks like a black hole. So how can we detect something we can't see? Well, the nice thing is that while we can't see the black hole, it is black, we can sure see the stuff falling into it, which happens to get very, very hot. So there's a couple of things we can see. We can see gravitational effects. These things have mass. They can orbit things. Things can orbit them. Also, they cause gravitational lensing, so we can see that. So if it's in a binary pair with another star, we can use Kepler's third law to determine the mass. Or if something is orbiting it, we can use Kepler's third law to figure out the mass. That's how the mass of the black hole at the center of our galaxy was figured out. So one of the first identified and best black hole candidates out there is Cygnus X1. It's a binary system, the unseen companion. So there's a big bright star and an unseen companion. It's about 15 times the mass of the sun. It's much too big to be a white dwarf for a neutron star. But we know it's very compact. There's ways to tell. And it's emitting X-rays, which is consistent with material falling into a black hole. So Cygnus X1 is almost certainly a black hole in a binary system. So how do we verify that something is a black hole? Well, the first thing we need to do is measure its mass. So we can use the orbital properties of its companion. When two things orbit each other, we can figure out the mass of the missing object by measuring the second orbiting object. And we can measure the velocity and distance of the gas orbiting it. So we can get information about it from there. And if it's a black hole, it's a black hole if it's not a star, and if its mass is bigger than about 3 times the mass of the sun, which is the limit for neutron stars. So if you have 10 to 15 times the mass of the sun, well, that's almost certainly a black hole. So to figure out that these black hole binary parameters exist, we can look at the effects they have on the star's orbit, and by radiation from infalling matter, you get these X-ray sources. So the X-ray source here is coincident with the visible star. And then this star is oscillating, it's a B star. And you can get some idea of what's going on. Some X-ray binaries contain compact acid objects of mass exceeding 3 times the solar mass that are likely to be black holes. One of these is Cygnus X1. It was one of the first identified, so it's the classic example that always gets used. So one of the famous ones is in the constellation Cygnus. The unseen companion is about 15 times the mass of the sun. It's a very strong solar candidate, black hole candidate. The visible partner is about 25 solar masses. The system total mass is about 35-ish solar masses. I think it's like 20 to 25, and so the partner is about 10 to 15 solar masses. There's hot gas that appears to be flowing from the visible star to an unseen companion. And the fact that the variations of that are very fast, turns out you can figure out the size of an object by looking at how fast it varies with time. Because if it was really big, it would take light longer to go from the far side to you. And that sort of spreads out the variations. So it's one of the ways you can study how things vary with time. So the short time scale variations indicate the source needs to be very small. This is more important for figuring out what's going on with actually supermassive black holes and active galaxies, but it is useful in general. So this is an artist's conception of the Cygnus X1 system. There's a B star companion. Material is being pulled off of it into a black hole. That is the X-ray source. There's an accretion disk of matter. So we can see X-rays being emitted from material that spirals into an accretion disk around the black hole. The gravity accelerates the material to high speeds. The friction heats it to high temperatures, billions of degrees. Additionally, there are supermassive black holes that exist at the centers of many galaxies. These are also seen through gravitational effects and X-ray emissions. So for example, the determination that we had a black hole at the center of our galaxy came from studying the orbits of stars around it in the center of our galaxy, which gave us a limit on the size and a mass. But it's also an X-ray source. It's called Sagittarius A star. It's primarily a radio source, but I mean, it's a bright source. And then lastly, just recently, we took a picture. This is the black hole in the center of galaxy. Is it 83 or 88? I can't remember. 87, M87. So this is the black hole in the center of the galaxy M87, which was the first one that was imaged. It's much bigger than the black hole in our galaxy, but they also went on to image a black hole in the supermassive black hole at the center of our galaxy. And this was done by doing interferometry with radio telescopes distributed around the entire world, generating a radio telescope effectively the size of the planet Earth. So this was a really impressive thing. And there's several other black hole candidates as well, with characteristics similar to Cygnus X1, and the centers of many galaxies contain supermassive black holes, which are at least 1 million solar masses. So this one in M87 is, I think, like 1 billion solar masses. The one in the center of our galaxy is about 4 million solar masses. They are not small. And recently we found some interesting evidence for intermediate-sized black holes. These are actually interesting because they're too big to be formed from stars, but they're too small. They're tiny compared to the supermassive black holes. These are like 100 to 1,000 solar masses. So these are one of the things where we don't really understand how these form. Part of it may be black hole mergers, because we've observed gravitational waves from black hole mergers. And some of those mergers are pretty big black holes. But yeah, we don't fully understand how intermediate-sized black holes form. We have an idea for smaller ones. We have an idea for really big ones. We don't have a good idea for the middle. So a black hole is an object whose escape velocity is greater than the speed of light. Black holes only have a few properties, including mass. The primary one that determines their properties is mass, and then there's also how much they're spinning and their charge. Usually their charge is pretty close to neutral, but or at least you would expect it to be, because generally they're going to pick most, on average, most matter is neutral. And they're going to grab matter from around them. But they often have quite a bit of angular momentum, and there's some interesting properties that come from a spinning black hole, because the spinning distorts the space-time in additional ways. It sort of drags the space-time around with the spinning, and you get even weirder effects. And there's evidence, so yeah, the large mass, however, doesn't make them a cosmic vacuum cleaner. They're just like any other massive object. And the evidence, far away at least. And there's evidence for both stellar-sized black holes and supermassive black holes. Now, the 2020 Nobel Prize in Physics was about black holes. They were for two discoveries. There was Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity. Roger Penrose, so black holes existed as a solution to the equations of general relativity, but until Roger Penrose worked out a way, it wasn't certain whether they could actually form. So it was uncertain, and that if you had, it wasn't certain whether to have something like a black hole form, you needed something that was like perfectly symmetrical or something like that. Roger Penrose showed that if you had sort of an irregularly shaped blob of stuff that collapsed, you would get a black hole. He was able to solve the equations of general relativity and show that even for something that wasn't, really nice, didn't have perfect symmetrical properties, but was like rough and irregular, you could get formation of a black hole. But black hole formation was robust. You didn't need special conditions for it to happen. And then Reinhard Genzel and Andrea Ghez ran two separate projects that were studying the supermassive black hole at the center of our galaxy, tracking things orbiting them. And so there is for the discovery of a supermassive compact object at the center of our galaxy. They don't specifically say it was a black hole because I think at the time of this, it hadn't strictly been confirmed that it was a black hole. They could just say it was supermassive and very small. And the only thing we knew of that could be that was a black hole. This is, and Reinhard Genzel ran the European study that was tracking with one set of telescopes. Andrea Ghez ran the American one. They were both studying the stuff orbiting around the black hole at the center of our galaxy, tracking the orbits and figuring out the size. Now, sometimes we get extreme events, crazy things, like black holes or neutron stars merging. And these generate gravitational waves, and in the case of neutron star mergers, also gamma ray bursts. I just recently ran across a video showing some modeling of a neutron star merger. But let's talk about one of the interesting things about this is because we have these incredibly massive objects merging, they end up orbiting each other very, very, very quickly. Orbiting each other very quickly, and then you end up with massive objects accelerating very quickly. And it turns out one of the predictions of general relativity is that if you accelerate a massive object, you'll get a gravitational wave or ripple in space-time. And in 2015, we finally managed to detect these. The problem is that these end up being, by the time they reach us, these are very, very small.
The direct detection of gravitational waves, first accomplished in 2015, offers astronomers an entirely new way to observe the universe. In this video, we'll briefly discuss what gravitational waves are and how they have been detected. The idea of gravitational waves comes directly from Einstein's general theory of relativity, which tells us that gravity arises from curvature of spacetime, which is curved by masses in much the same way that heavy weights curve a taut rubber sheet, except in two more dimensions. In the rubber sheet analogy, the curvature created by a massive object like the Sun determines the paths of objects orbiting around the Sun. Moreover, although not shown in this diagram, the orbiting masses must themselves press down on the rubber sheet. Animating the analogy, a planet orbiting the Sun must make a small depression in the rubber sheet that moves with the planet. Much like swirling your finger in a pond, this moving mass should generate ripples moving outward across the rubber sheet. These ripples are what Einstein identified as gravitational waves. However, the equations of general relativity show these waves to be so weak that Einstein himself doubted we'd ever be able to detect them or notice their effects. But Einstein not only underestimated our technological advance, he also didn't know about objects like neutron stars and black holes, which can generate much stronger gravitational waves. This next animation shows a rubber sheet analogy for a binary neutron star system in which two neutron stars are orbiting very close to one another. The ripples represent the gravitational waves, and as the animation tries to show, these waves carry energy away from the system. Because energy must be conserved, the energy carried away from the system must come at the expense of the system's orbital energy, and this should cause the orbits to gradually decay. In other words, the orbital period of the binary neutron star should gradually shorten in a way that can be precisely predicted by the equations of general relativity. In fact, this is how astronomers first discovered strong evidence that gravitational waves really exist. This graph shows data for the first discovered neutron star binary. The red curve shows the orbital decay predicted by Einstein's equations, and the dots are actual data points. The near-perfect match tells us that the system really is losing energy to gravitational waves, an idea that has been confirmed by the discovery of several similar systems that show the same type of evidence. However, strong as this evidence is, it is still indirect. To detect gravitational waves directly, scientists realized that they'd need both a stronger signal and an extremely sensitive detector. For the stronger signal, binary neutron star systems point the way, as you can see by answering this question. What should you expect to eventually happen to a neutron star binary system? Will the orbital decay continue forever? Will the orbits eventually stabilize? Will the neutron stars eventually spiral into each other? Or will they eventually fly away from each other? The answer is C. The orbital decay means the two neutron stars gradually get closer together, which in turn means the gravitational waves emitted by the system become stronger. As a result, the orbital decay will accelerate until the neutron stars spiral into each other. This next animation shows the accelerating decay of the orbits as the emitted gravitational waves strengthen. Moreover, the final merger of the neutron stars should emit a particularly strong pulse of gravitational waves. The same type of pulse can come from the merger of two orbiting black holes. Both have now been detected. The instrument that first detected gravitational waves is called LIGO, which stands for the Laser Interferometer Gravitational Wave Observatory. This aerial view shows the LIGO detector in Hanford, Washington. Notice the two arms arranged in an L shape, each 4 kilometers long. According to general relativity, this arrangement should mean that as a gravitational wave passes by, one arm should very slightly shorten while the other slightly lengthens. This animation shows the idea, with the red lines indicating the laser light that is used to measure extremely tiny changes in the lengths of the arms. In fact, LIGO is so sensitive that it can measure changes in length that are far smaller than the size of a proton. With such tiny changes in length, you might wonder how scientists could ever be confident that a signal was real and not an artifact of some local event. The answer is that LIGO has a second detector, located in Livingston, Louisiana, so scientists can be confident a signal is real if both detectors record the same signal. Because relativity predicts that gravitational waves should travel at the speed of light, one detector should receive a passing signal slightly before the other. This graph shows the first such detection, made in 2015. Notice the match between the signal received at the Hanford and Livingston detectors. Using the equations of general relativity, scientists were able to conclude that this signal came from the merger of two black holes in a galaxy about 1.3 billion light-years away. Gravitational waves are fundamentally different from any form of light, and they therefore give us an entirely new way to study the universe, and scientists expect rapid progress in their study. Already, LIGO has been joined by a third detector called Virgo, which is located in Italy. Just shortly after Virgo came online in 2017, the three observatories detected the first unambiguous gravitational wave signal from the merger of two neutron stars in a galaxy about 130 million light-years away. Moreover, having 3 detectors allowed scientists to pinpoint the location of the neutron-star merger well enough for follow-up observations in light across the spectrum, from radio waves through gamma rays. These early successes of gravitational wave astronomy are spurring new technological developments that should further improve our capabilities, and you should watch the news to learn of the many gravitational wave discoveries sure to come in the future.
So there's a ton of these now. There's a whole big list of them that you can see. They take forever to verify because, again, these are tiny changes. But like the possibility, like I think there's a big list on Wikipedia. There's dozens of them. They're surprisingly more common than we thought. So one of the funny things is that once they upgraded LIGO to be sensitive enough to actually pull this off. So LIGO had been around for a while actually, and they just finished an upgrade in 2015. Literally that first observation, that was like the day after they turned it on for that run. They were not expecting it so quick. And one of the interesting things about this is because they're basically vibrations, you can actually listen to them as sound. Let me see if I can pull up. Because they happen to be like let me just pull up. So here, this is the sound of 2 black holes colliding. Let's see if we can find a neutron star collision. There. Oh, this is a simulation. Let's see if we can get one from actual data. Because I know there's some out there. Oh well. But yeah, you can actually listen to the sound of them because the frequencies are pretty much audible frequencies. So when neutron stars, and they make sort of a chirp. When neutron stars merge, this is the detection of the gravitational wave signal from 2 neutron stars. And the similar detection of the visible light from it. And gamma ray burst from the Fermi Observatory as well. So we were able to detect this neutron star collision in a few different ways. So 2 neutron stars in a close orbit will emit gravitational waves and spiral together. Here is theory versus observation for one such system. We're watching these spiraling closer and closer, faster and faster. And then when they merge, you get this chirp. These faster and faster merger and then a burst. So gravitational waves as well as a gamma ray burst in light across the electromagnetic spectrum we're seeing coming from a neutron star merger in 2017. Now when black holes merge, you also get gravitational waves. And you mainly get a bunch of energy, a lot of the mass gets released as gravitational waves, as energy, and then you get a new bigger black hole. So the merger of 2 black holes produces a burst of gravitational waves. The advanced LIGO experiments saw such waves coming from a merger about 13 billion light years away in 2015. gravitational waves were predicted by general relativity. So any object with mass that is accelerating will produce gravitational waves, but they're tiny. Gravitational force is weak, so gravitational waves are very hard to detect. We have detected them indirectly from a binary pulsar. The orbit slows by the exact amount described by general relativity. And finally, we've detected them directly with LIGO. Only recently we've been able to directly detect these waves with LIGO. You need a strong source of gravitational waves for it to be detected. So far, we've only detected coalescing black holes and neutron stars. There are plans to build better gravitational wave detectors that can detect other events that don't make as dramatic gravitational waves. I think there's some trying to do hypernova and other things. So coalescing black stars and neutron stars, and possibly the massive star implosion to form a black hole. We may have detected that. That's one of the things they're trying to detect better. So this is LIGO, the Laser Interferometer Gravitational Wave Observatory. It uses multiple sites to eliminate local effects because this thing is so, they're looking at a change in distance of less than a proton over a length of 4 kilometers. It's kind of crazy. So multiple sites eliminate local effects. 2015, there was a detection of gravitational waves, and the distance needs to be measured to an accuracy of a 10,000th the diameter of a proton. This thing is one of the most accurate, most precise devices ever built. It's kind of nuts. So the problem is that anything going on outside creates something that's probably a bigger signal than the gravitational wave. Like a truck driving down the road nearby is a bigger signal than the gravitational wave. So cleaning all of that out is really tricky. And you need to use multiple sites far away from each other to make sure what you're seeing is actually a gravitational wave and not something local. So that's why LIGO has 2 sites, one in Washington and one in Louisiana, basically opposite sides of the country. And there's now a 3rd site, Virgo, in Italy. I think there's a plan to build one in Japan as well, but I'm not 100% sure. So on September 14th, 2015, they detected GW 150914, which is gravitational wave 2015 September 14. It was announced on February 11th, 2016. And the observations were consistent with the merger of 2 black holes. One 20 solar masses and the other 36 solar masses. They merged about 1.3 billion years ago. So they're a long way away. And there have been many more detections over the past several years. Like there's a huge list of these that you can look up. They just take a while to confirm because people are careful. So dozens have now been detected. There have been observations from 2015 to 2020. New observations are scheduled to start in 2023. There are many black hole mergers and some confirmed neutron star mergers as well. And they're sort of spread across the sky. They're all in distant galaxies. LISA is a gravitational wave detector in space. It's the Laser Interferometer Space Antenna. It consists of like 3 satellites in a triangle 25 million kilometers on a side, acting as a massive laser interferometer. It's planned to launch in 2037. And this is hoping to detect mergers from supermassive black holes that are even more distant in the past. So even further away, so the signals will be weaker. So gravitational waves are produced by the motion of any massive objects. They were first detected in 2015 by LIGO. There have been more detections since that time. You can only detect massive objects now, but future improvements will likely allow for the detection of less massive objects. We're working on it, but it's hard because the variations from gravitational waves are tiny. Lastly, let's talk a bit about special relativity. So this was put forth by Albert Einstein in 1905. It was a new description of motion. So Newton's laws of motion work in almost every situation, but it starts to break down at very high speeds, i.e., a significant portion of the speed of light. So one of the big motivators for this was that it was up until 1890 or so, right around 1887, it was thought light needed some medium to travel through. It was a wave, it traveled through something because every other wave we know of travels through something. So if there's a medium it's traveling through, the Earth is moving, the Earth will be moving through this medium. We should be able to detect a difference in the speed of light based on how we're moving through the medium. This would be the case for any other wave that travels through a medium. If you're moving through the medium, there'll be a difference in speed going with the medium or going at right angles to the medium. So Michelson and Morley designed an experiment to test this by measuring a light beam traveling through the ether in different directions. They have an interferometer. This is the interferometer. The idea is that you are measuring how fast it takes light to travel one leg of this interferometer versus the other leg that are at right angles to each other. And then the light is combining and interfering. And the idea was, if you're in a medium, if you rotate the whole thing, your interference pattern should change. Because the speeds in the two legs will change, so the waves will arrive at different times, so the way they interfere will change. So they have this massive slab with the interferometer on it, and it is floating in a pool of mercury that allows them to rotate the whole thing. And they found no difference when they rotated it. There was no difference in the speed of light depending on direction. When they knew the Earth was moving. So this was a big issue. Like, why is light traveling at the same speed in all directions? So special relativity put forth this idea that there is no absolute frame of reference. As long as motion is uniform, you cannot tell who is moving. Either you are moving and the other guy is standing still, or they're moving and you're standing still, and there's no way to tell the difference. And the laws of physics are the same in each reference frame. And lastly, the thing that adds the spice to this is that the speed of light is constant and the same value for all observers, regardless of their motion. So what happens is when you get really big velocities, velocities start to add different. So these two guys, one of them seems to be moving, the other one seems to be standing still, will both measure the same speed of light. And I have no way to differentiate who's moving and who's standing still. And this has some interesting consequences. A number of things become relative. One of the most interesting is simultaneity. Whether events are simultaneous or what order they happen in, if they're far enough apart, depends on the motion of the observer. So if you're moving with a velocity 0, they're simultaneous. With 0.3 c, c happens first. With minus 0.5 c, a happens first. That's one of the weird things. There's also time dilation. As you observe someone moving faster, their clocks appear to slow down. This is observed with muons produced in the upper atmosphere. So muons have a very short lifetime. They're radioactive, they fall apart. But muons produced in the upper atmosphere make it to Earth, and the time it takes them to make it to Earth should be longer than their lifetime. Like we know how fast they're going. We can figure out how long it took them to make it to the surface of the Earth. So the fact that their clock slows down can be observed because they make it down here on Earth. And you can just do a test for yourself. You can build a muon detector. There are muons coming down all the time. And so you can detect some muons. They're not, muon detectors, it's not actually all that complicated. Also, this is something we have to correct for with GPS satellites. So GPS satellites have to both correct for time dilation from speed and gravity. They happen to go in opposite directions, which makes things a little better, but there is a net correction that needs to be made. There's also length contraction. Objects moving at high speeds will appear shortened in the direction of motion. And all of these have been observed. And the effect gets bigger the closer you get to the speed of light. So this is sort of the scale of the effect. So you get effects of a factor of 2 around a little over 0.85. 3 is 0.9 something. 4, you can see how it gets bigger and bigger as you get closer and closer to the speed of light. And here is length contraction. So the thing is that you can work out these ideas about causality. You can make something called a light cone, where you can draw space represented by the x-axis and time by the y-axis. The current location is the origin. This blue line is the speed of light. The only things you can interact with are things close enough to you in position that you can reach them at a speed less than the speed of light. So you can have no causal connection with C over here, but you can with B. So you can travel within the light shaded region, but you can't go in the dark shaded region. You would need faster than light travel. So A can cause B, but not C. And if you're moving fast enough, you can actually have C happen before A. So you can distort what's going on about simultaneity, the order of events in this area outside of causality. There's no way for B to happen before it. There's some interesting paradoxes, like the ladder paradox, where if you have a rapidly moving ladder, it would be shortened and fit in a smaller garage. However, because motion is relative, from the point of view of the ladder, the garage would be shortened. So how do you fit in? Well, what happens is the closing of the door stops being simultaneous. So if you consider a stationary ladder and a moving garage, the garage is shortened and the ladder shouldn't fit. The solution is the end of simultaneity. The doors don't end up closed at the same time. So in a moving garage, we have a problem. Well, the solution is that the front and back of the ladder are not in the garage simultaneously from one point of view, but not from another. For one observer, the garage, both garage doors are closed at the same time. For the other, they close at different times. And if you want to work this all out, the math for special relativity is relatively straightforward. It's all just high school level algebra. The main formula is multiplied or divided by square root of 1 minus b squared over c squared. And this is numeracy. Well, but Yeah. Motion at high speeds. So the special relativity describes motion at speeds near the speed of light. Motion at high speeds cause time dilation and length contraction, as well as causality issues. And paradoxes like the latter paradox occur because simultaneity depends on the reference frame. And to get a little more intuitive understanding, there's a nice series of videos by Minute Physics about special relativity, because you sort of an idea of what's going on with the way that things change with velocity. So the summary of the chapter: a supernova can leave behind a neutron star. Neutron stars are very dense. They spin rapidly. They have intense magnetic fields. They may appear as pulsars due to the lighthouse effect. A neutron star in a close binary may become an X-ray burster or a millisecond pulsar. Gamma ray bursts are probably due to two neutron stars colliding or to hypernova. If the core remnant is more than about 3 solar masses, it will collapse into a black hole. We need general relativity to describe black holes. It describes gravity as the warping of space-time, and anything entering within the event horizon of a black hole cannot escape. And the distance from the event horizon to a singularity is called the Schwarzschild radius. A distant observer would see an object entering a black hole to be subject to extreme gravitational redshift and time dilation, and material approaching a black hole will emit strong X-rays, and a few such X-ray sources have been found and are black hole candidates. We've also observed supermassive black holes in the centers of galaxies. So, just a reminder, worksheets 23 through 29 are going to be due on the 2nd. Homework number 4 is due on the 2nd. Exam number 4 is on the 2nd of December. If you missed the exam on Thursday, please come talk to me. You can do it today. Or on Thursday, come talk to me. And your presentations and papers for the semester project are due on the 4th. So we're going to have exam number 4 and then the presentations. But we still have a bit of time left. So let's begin talking about our home galaxy. Let me just quickly fix this. Yeah. So, the Milky Way galaxy is the galaxy we live in. It is a spiral galaxy. So let's talk about the structure of our galaxy. It's actually kind of tricky to figure out the structure of our galaxy because we're in the middle of it, which makes it somewhat hard to observe. But we have determined the structure of our galaxy by observing various aspects of it, and worked out where the center is, worked out the extent of it, and eventually we've got a decent idea of what type of galaxy it is and what it looks like.
Welcome to an overview of our galaxy. In this video, we'll introduce a few of the key learning objectives of the chapter. In particular, we'll explain how the Milky Way's shape reflects its patterns of star motion, describe the star-gas-star cycle that enriches the Milky Way with the elements needed for life, and describe how the properties of disk and halo stars suggest a basic picture of galaxy formation. Our Milky Way galaxy, shown here as an artist's conception of what it might look like from outside, is a vast collection of stars and gas clouds, all held together by gravity. Our solar system resides about halfway out, from the center to the edge of the disk. From this vantage point, we can only see the galaxy from the inside, and with visible light it appears as shown in this view that represents the entire sky, in much the same way that a map of the world shows the entire surface of a globe. The horizontal swath is our view into the disk of our galaxy, with the direction toward the galactic center in the middle. Notice the many dark, dusty clouds that prevent us from seeing very deeply into the disk with visible light. This limitation explains not only why it took astronomers so long to learn the size and structure of our galaxy, but also why we're still in the process of understanding its origins and operation. Nevertheless, we now know that our galaxy is essentially a giant ecosystem in which matter produced in past generations of stars is recycled into new generations. Without this galactic recycling, we would not be here today. Let's begin with an overview of our galaxy's structure. From the outside, the galaxy appears as a fairly flat disk, marked by prominent spiral arms and a bright central bulge. As discussed in your textbook and a separate narrated figure, strong evidence indicates that at its very center, the bulge harbors a 4 million solar mass black hole. Surrounding the disk is the roughly spherical region that we call the halo, which is nearly invisible except for the presence of globular clusters of stars. We can show the galaxy's proportions better by switching to a painting that shows an edge-on view, where we see that the disk is about 100,000 light-years in diameter, but only about 1,000 light-years thick. Notice again that the halo is nearly invisible except for its bright globular clusters. The shapes of the different parts of our galaxy arise from the orbits of stars. Stars in the disk orbit in orderly circles with just a little bit of up and down motion that gives the disk its thickness. In contrast, stars in the halo have orbits that are randomly oriented. Bulge star orbits, not shown here, have a mixture of disk and halo characteristics. Putting things together, these differing orbits give our galaxy its flat disk and a more rounded bulge and halo. Gas resides almost exclusively in the disk, and we refer to all the gas and dust that resides between stars as the interstellar medium. The disk is therefore where galactic recycling takes place.
So let's talk about the structure of our galaxy and what it looks like. So the Milky Way galaxy appears in our sky as a faint band of light. You can see here. From Earth, we see few stars when looking out of the galaxy. Out of the galaxy in the directions of the red arrows. Up and down, and many of them looking in the directions of the blue and white arrows. So if you look into the plane of the galaxy, you see lots of stars, and you see the Milky Way across the sky. And if you look perpendicular to that, you see very few stars. So this is, an image towards the center of the Milky Way, the white in the direction of the white arrow shown. So in the night sky, this is the Milky Way we see. And you can see that even here. So here's the Milky Way in the sky. Now, we find that in the center, towards the center of the galaxy, there's these dusty gas clouds that obscure our view of the center because they absorb visible light. This is the interstellar medium that makes new star systems. Kind of hard to observe the center of the galaxy just because there's a lot of stuff in. That is, for example, why the first image of a black hole wasn't one in our galaxy. It was an even bigger one in another galaxy that was about the same size in the sky, but was easier to look at because there was less stuff in the way. Our galaxy is a spiral galaxy. Specifically, it is a barred spiral galaxy, which I don't think any of these are. So this is the nearby Andromeda galaxy, which is not a barred spiral galaxy, but it is one of the very nearby galaxies. It's also got a bulge and a disk. Here's another nearby galaxy seen face on, and one seen edge on. Ours looks a little different than these because it has more of a bar across the center. Now, how did we determine the structure of our galaxy? That was actually quite tricky because we're stuck inside of it. So how could you determine the shape and extent of a building if you were stuck in a single room? It's hard to do. It started with William Herschel in 1785, who counted stars in various directions to get the first rough map of the Milky Way. And he ended up with the sun at the center. And that's because really what it was counting is, how far you could see in every direction. And when you run into gas and dust in various directions. And that sort of cuts you off. So he wasn't aware that most of the galaxy, particularly the center, is blocked from our view from vast clouds of gas and dust. So early models of the galaxy placed the sun near the center of a relatively small system. Herschel's measurements were quite limited. He didn't know about dust, and he limited the part of the galaxy he could actually see. Harlow Shapley started studying globular clusters. These happen to be distributed around the galaxy in a spherical halo and give you a better idea of the actual extent of the galaxy. So here is a map of the various globular clusters that Shipley was studying. And the dark splotch here is Herschel's old diagram centered on the sun. And he was able to figure out, the center of the galaxy was over here, how far we were from the center, and get a much better idea of the scale of the galaxy. So here's an artist's conception of the various parts of our galaxy and the position of our sun. There's the galactic center with the galactic bulge. There's the galactic disk. Here's our sun out towards the edge, and various stars orbiting around. We see our galaxy edge on. It has three primary features. There's a few primary features: the disk, the bulge, the halo around, and globular clusters. And if we could view the Milky Way from above, we would see it look something like this. There's a bulge with bars and spiral arms coming off the ends of those bars. And I'm going to stop there for now. We will continue this on Thursday. Please remember, if you haven't taken the test, come in, take the test. You can do it during class or after class. I'm going to end the meeting. And if you haven't signed in, make sure to sign in.